All right. What we're going to do here is we're going to predict spectra, photoelectron spectra data or graphs, and interpret them and explain any differences and use them to identify an element. All right. So here's our machine. And what the machine does is it spits out this graph, and we want to be able to predict what these graphs are going to look like. Now, this is a mixture of something. It could be an alloy. I'm not exactly sure, but you can see there are various different elements. We are going to stick to mainly elements in terms of what's going to be expected of you. Now, when you do this, you have to remember that electrons fill these orbitals in a pattern, because you're sort of going to be unpacking the pattern when you look at spectra. All right, so here's one. This is carbon, all right? Now we know carbon's got this electron configuration, it's got 6 electrons. So whatever our graph looks like, it should accommodate for all of these, and it's got 2 energy levels, all right? So it should have a difference, 2 different areas where the electrons are placed. This one there's going to be a peak here for 2. That's the 1s, and then some over 1 over there. Let's just call that a peak. This would be the 2s, and then there would be the 2p that would go up there like that. All right, that's what it would look like. Now, what would this one look like? This is helium. All right, here's helium's electron configuration. So if you want, pause your video and draw it. All right, guess what you're going to think it's going to look like. Is it going to be closer to the origin, or is it going to take less energy? What do you think? All right, I'm ready to go. Here we go. So this is what helium is going to look like. All right, a peak of 2. Now, if I were to superimpose carbon, carbon's 1s would look like this, and its 2p's would look like, 2s's would look like that, and here's its 2p's. All right, so that's what it would look like. And one of our goals is to figure out why. Why would this happen like this? And here's a third element. This is fluorine, all right? Fluorine's got the 1s. That's going to even be further over if you had them all on the same scale. It may not be if you had them all on the same scale, but it's going to have one peak for the 1s, and then it's going to have another peak for the 2s, and then an even bigger peak for the 2p that goes all the way up to 7. All right. Now, so you want to be able to draw these, and you're not going to necessarily be able to know how much energy, but you should be able to know relative to one another where any orbital is and which orbital is which peak. All right, now, what element is this? Now we're going to actually look at what the data looks like and try to, wait a second. All right, what element is this? All right, it's got 1 proton, it's hydrogen. All right, there's it is. So its graph is going to have 1 peak. It's going to have for the 1s electron, and there it is. All right. Now, what element is this? This is atomic number 7. So this is nitrogen. All right. How many peaks is it going to have? It's going to have 3 peaks. All right. And if you notice, the nitrogen's peaks, this 1s, the 1.3 megajoules per mole, is a lot significantly different in nitrogen. All right. It's almost 40 times stronger. All right. And we're going to account for that in a moment. Now, here's one. What element is this? All right. You go ahead and pause the video if you want to figure it out, and try to label what peak is what orbital. All right. All right, here we go. Remember, it's good to think about the nucleus being here. All right. The first thing it's going to encounter is the 1s2, the 2p, 2s2. Now that's 1, 2, 3, 4, 5, 6. 2p6, 3s2, 2p1. What element is this? It's aluminum. All right, because it's got 13 electrons. Oh, and that's not 2p, it's 3p. 3p, 3po. It's got so aluminum's got 13 electrons, and you would simply go to periodic table. All right, here you look, 13 there's aluminum. Okay, now where's my screen? There. Okay, now I don't know if it worked, if it cut out or not. Should have, but I just looked up on. I knew off the top of my head, but I looked up the atomic number 13. Okay, now here we've got 3 different elements, and from here we're going to try to explain why they're different. Their graphs are different. If you look at the graphs of hydrogen and nitrogen, you're going to see the 1s orbital is in both of them, or the respective 1s electrons. But why is it significantly larger to remove the electrons with nitrogen than it is with hydrogen? All right. And furthermore, if you look at aluminum, you're going to notice that its electrons, or its 1s electrons, are 5 times, or roughly 4 times greater than nitrogen's. Why is this? Well, it all has to do with the nuclear charge. These inner electrons, or core electrons, are so much more tightly bound because the nuclear charge in the atom, or in the nucleus, is so much more significant. So here in aluminum, we've got 13 protons to these 2 electrons, whereas in hydrogen, you only have 1 proton. So all the differences in all of these graphs and where the peaks are can be explained in terms of the nuclear charge and the distances. And in this case, the distances is saying relatively, I mean, they may be a little bit different, but it's relatively the same, but the nuclear charge is going so much greater, therefore the binding energy would be more because it takes more energy to remove it. All right, so that's how the peaks are different and why the peaks are different. All right, thanks, and I hope this was helpful. Let me know if I can help. All right, have a good day.